Let's come to question number 5 now. A meter stick is held vertically with one end on the floor and is then allowed to fall. If the end touching the floor is not allowed to slip, the other end will hit the ground with a velocity of A under root of 10, B under root 30, C under root 20 or D under root 40.
So let's see this question. Now we know nothing about the stick. However, the question very smartly tells us that it's a meter stick. So now we know that this length L is equal to 1 meter. Right? So now if we try to solve this question somehow, we know that there are no forces except for the gravitational force and the frictional force. Now any torque which is provided to this meter stick about, let's assume this point to be O, will only be because of the gravitational force, since any frictional force which exists will be applied on point O and the distance is 0.
Right.
So the torque caused by the frictional force is 0.
So we don't need to worry about the friction force at all when we talk about the torque.
Right. Now, if you see the gravitational force, for example, let us assume different moments of time. The gravitational force over here will be like this, over here like this, over here like this. So you see that this angle keeps on changing, so integrating the gravitational force with the displacement, etc., will be a lot of problem. So we can't find the angular momentum. So here we'll try to conserve the energy. Since the energy will obviously be conserved, the angular momentum won't be, since there's a torque due to the gravitational force.
But there's a friction force acting, so how can the energy be conserved?
Good question. Now here you see, even if a frictional force is being applied, this point at which the frictional force is applied is not moving. So the displacement of the application of force is 0. Right? So the
no
work done. Yeah, no work is done by the frictional force. Anything which is done only by the gravitational force. So here we can see that the initial potential energy of this meter stick will be equal to mg. Let's write it down. The initial potential energy of the stick will be equal to mg into L by 2, and the final potential energy final will be equal to 0.
Why so?
It's lying on the ground. The center of mass is on the ground. If we assume this to be the reference point.
Oh, right.
0. So now here we see that when it is falling down, all of this potential energy which we have mg L by 2 will be converted into its rotational motion, as there is no linear motion around here. Right? So we'll equate this to the rotational kinetic energy of this body. Now we know that mg L by 2 is the initial energy. This will be equal to half into I into omega square. This is the expression for the rotational kinetic energy, basically, as we had learned in the introduction. Right? Now we know that the moment of inertia of this rod about an axis passing through its edge is given to us by m L square by 3. This we had calculated in the introduction, as we remember.
This we need to memorize.
Right. Into omega square. This from this expression we can easily find out the value of omega. Right?
Which is the angular velocity.
Yeah. Which is the part which is asked into the question. So here we find out omega to be equal to under root 3g by L, and putting in the values we find out that omega is equal to under root 30, which is option number B. So basically this basic question was chosen to understand the concept that here we can't use a conservation of angular momentum, as there is an external torque which is not even constant. So integrating it and going into all that problem is not an option, since when we are concentrating on IIT problems, we need speed over here. We need quick thinking. So what we think over here is we'll easily conserve the energy. Let's not get into angular momentum.
Right. Okay, so in this question, we saw that we can find out the angular velocity omega by simply equating the energy, the loss in potential energy to the gain in rotational energy. Right. So this was question number 5. Moving on to question number 6. A disc at rest on the top of an inclined plane of height h rolls down without slipping and acquires a velocity v on reaching the bottom. If the same disk slides down along a smooth incline and acquires the same velocity on reaching the bottom, the height of the smooth incline is A h by 3, B h by 2, C 2h by 3 or D h.
Okay, so we'll start this problem with concentrating on a very important concept, which is the concept of rolling. Now, the concept of rolling says that when any object is rolling on any incline or any surface, the point of contact will always be at rest. This is the concept of rolling. So here, if you see that the body is coming down an incline which has some friction, we'll see that the work done by the friction on the body will be zero, as the point of contact where the frictional force is applied is always at rest. Right? So we'll go ahead and try to solve this problem by using conservation of energy, as there is no external work done by frictional force. The only work done is by the gravitational force, which we can use as the potential energy. So here we understand that the loss in potential energy of this body while coming down the incline. Let's draw the incline and draw the body. And while this body is coming down, the loss in the kinetic energy, the loss in the potential energy, will be equal to the gain in the kinetic energy of the body. Now, here we need to remember one thing. Since there is frictional force, there will be torque applied on this body. Since the torque will be the force into the distance from the center of mass. So, here we see that there will be torque on the body, and so there will always be rotation. And so when we find out the kinetic energy, we need to remember that there is the rotational kinetic energy which we need to include. So let's write down the energy conservation equation. The initial potential energy will be equal to mgh. Simple. This will be equal to the kinetic energy of the entire body when it comes to the bottom of this inclined plane, which will be equal to half into m into v square, which is the translational kinetic energy of this body, plus the rotational kinetic energy. This is the new concept which we are learning in rotational motion as against the translational motion which we used to study earlier. Right. So this is a new added term over here which we have. This now we know m, we know the g, we know h, we also know I. How? It's very simple. It's a basic disk. So the moment of inertia will be equal to m. Let's write it down. I equal to m into r square by 2. We know m, we know r.
In this case, we are saying that we are talking about the point of contact, right? So shouldn't we calculate the moment of inertia from along, as in about an axis passing through the point of contact, and then use it?
Okay, good question over here. As we had known earlier that we always consider the center of mass point. So we see that the body is rotating about the center of mass over here, and we are using the kinetic energy, the translational kinetic energy about the center of mass. So what we do over here is we find the translational kinetic energy of the body about this point, which is half into mv square, plus the rotational kinetic energy also about this point. Because we are finding the translation through this point, we take the rotation to the same point. We can't take it about two different points and complicate it.
So in energy conservation, we will be talking about the center of mass.
Right. We are taking everything about the center of mass. We won't go over here and there and all those bodies. So now we know all the values. So now here we know all the values, and we can basically find out the expression for v square by cancelling all the remaining variables and stuff from this equation which we have written over here and inputting the value of I from here. When we do this, we find out that v square is equal to 4gh by 3. Now you might be thinking, why have I found out v square and not v? Okay, so here the concept which lies is, the question says that the velocity acquired coming down the smooth incline is same as the velocity acquired while coming down the rough incline. So here we needed an expression for velocity, we found that out. Now we need to find the height of the smooth inclined plane. So that we can find out by again using the conservation of energy and assuming the height of the smooth inclined plane to be capital H. Now if we assume the height of the smooth plane to be capital H, in that case the conservation of energy will give us mgh equal to half into m into v2 square. Let's assume the new velocity to be v2. But we know that v2 is equal to v as mentioned in the question.
Right.
So let's write down V2 square equal to V square equal to 4GH by 3. Right?
Okay.
Now you might want to ask me over here, why have I not taken the rotational kinetic energy in this expression?
Yeah, exactly.
Right?
Yeah.
Now here, as you have seen, the new inclined plane, the second inclined plane, is a smooth inclined plane. So
Okay.
there is no frictional force, no torque about the center of mass, and so no rotation.
Right. Because the gravitational force always passes through the center.
Center of mass, exactly.
Right.
So there is no torque, no rotation, no rotational kinetic energy. Now we easily input the value of V square from the expression which we have found out over here. We cancel out M, we find out H. Very simple. H will be coming out as 2H by 3. Here you
Right.
can see that now we have found out H, which was asked in the question. The option C is the correct option. I would like to elaborate a bit over here. Now we see that coming down a smooth incline, the height which we required for acquiring the same velocity was 2H by 3.
Right.
Here you can see that 1/3 energy in the initial case was going into putting in the rotational kinetic energy of the body.
Right.
Right? So here we correlate the energy which is related to the rotation of a body as against the translational motion.
Right. So in this question we saw translational and rotational motion combined together.
Right.
But we dealt with mostly energy related phenomena.
And
right.
we learned the concept of rotation.
And we learned the concept of rolling.
Right.
So one important point in this question is that when a sphere or when a body is rolling, then the point of contact is always at rest. Right? So we can use the energy conservation because the friction force is applied at the point of contact and the displacement of that point is 0. So work done by friction is 0. Right?
Here you need to remember that the point of contact is at rest with respect to the surface on which the body is rolling.
Right. So that was question number 6. Let's come to question number 7 now. A block X of mass 0.5 kilograms is held by a long massless string on a frictionless inclined plane of inclination 30 degrees to the horizontal. The string is wound on a uniform solid cylindrical drum Y of mass 2 kg and of radius 0.2 meters as shown in the figure. The drum is given an initial angular velocity such that the block X starts moving up the plane. A. Find the tension in the string during the motion. B. At a certain instant of time, the magnitude of the angular velocity of y is 10 radian per second. Calculate the distance traveled by x from that instant of time until it comes to rest. So it seems like a very lengthy, very complicated problem to me, but we'll go through the solution and let's see.
So here we see that we have a small body which is connected to a rolling drum. So what we'll do is basically we'll assume a few tension and acceleration quantities and we'll equate them. For example, if we are assuming that this body is going up with an acceleration a, we know that this point will go with an acceleration of a since they are connected to the same string. We'll use this concept to find the answer for this question.
Okay.
So for this, let's first draw the free body diagram for this body x. If we have this body x over here, the forces acting on this body are in this direction mg sine 30 degrees. The 30 degrees is the angle, and on this direction the force due to the string, which is the tension T.
Right.
Let us assume that this body is accelerating in the upward direction. If our assumption is wrong, our answer will come out to be a negative quantity. So
right.
we can assume it to be in any direction. So let us assume that to be a. Now we write down the equation for this body in the direction which is parallel to the surface of the incline. So that will give us T minus mg sine 30 will be equal to ma. Very simple.
Right.
From here we'll find out that a is equal to T by m minus g by 2. Right?
Okay.
So here we know the value of a now. Now let us take the drum. For the drum, we have a tension T acting over here, and there's no other force. Right?
Yeah, there'll be a hinge force which will be acting towards, as in at the center.
At the center, so it won't make any difference. There will be hinge force.
Okay, we are going to talk about the rotation motion. Right.
So since it is only rotating, there will be no effect of all these forces acting on the center of the drum.
Right.
So we consider only the tension over here. So now we know that the moment of inertia of this drum about an axis passing through the point, passing through its center, will be equal to m into r square by 2. Simple. We knew this from the introduction. Right. The torque on the drum will be only because of the tension in the string, which is T. Right. So the torque will be equal to T into R. Right. The force into the distance from the center. Very simple. Now we know the moment of inertia, we know the torque. Finding the angular acceleration, very simple. Alpha equal to torque divided by I. As we know from translation motion, acceleration is force by mass. Similarly over here, angular acceleration is angular force, which is the torque upon the moment of inertia. Right. Putting in the values from the above equations, we find out that this alpha is equal to 2t by mr. Now the point, the acceleration of this point will be equal to r into alpha. Right. This is the angular acceleration alpha, and the distance of this point is r. So the acceleration of this point, let us say a. Acceleration of a will be equal to 2t by m. Right. Now what we need to concentrate over here is, since the force is in this direction, the torque will be in this direction. Right. However, since the body is moving up, as said in the question, this drum is rotating in this direction, omega. Right. So the acceleration of this point, we know now, is in this direction, 2t by m. Right. Now, as we had seen over here, the acceleration in the same direction need to be same. Right. The string needs to be moving into the same direction. However, here we have seen that this a is the a for this body. The a is in the right direction. However, for this drum, a is coming out to be in this direction, which is the wrong direction. Right?
So the body will move down?
No. So here what we'll do is, while equating both the accelerations, we'll put a negative sign in front of a, this one. Right. So now we have found a in this direction.
So for that, shouldn't we assume a positive direction, let's say upward, so that so that we don't make such errors? Because people tend to make mistakes about signs and directions, right? And it can always be avoided if you assume a certain direction as positive. Right.
So if we assume this direction to be positive, we know that this a is equal to t by m minus g by 2, and over here we find that this a is minus 2t by m. I hope the negative sign over here is clear to you.
Right. It is.
So now we go on and equate both the accelerations, as we'll write it down as minus 2t by m equal to this acceleration which we found out over here, t by m minus g by 2. Writing it down, t by m minus g by 2. Now we can easily solve this simple equation for t, because we know g, we know capital M over here, we know the small m. And solving this equation, we'll find that t is equal to g m by 2m plus 4m. This expression can be easily found out. Putting in the values for g, capital M, small m into this expression will give us the tension as 1.63 newtons. Now we come to part B of the question. Now over here we need to find the displacement of the body until it comes to rest. So for that, we know that the deceleration d, let's take the deceleration to be d, is equal to r into alpha, which will be equal to 0.2 into 8.15, which will be equal to 1.63 meters per second square. And we also know the initial velocity v, which will be equal to r into omega, which will be equal to 0.2 into 10 equal to 2 meters per second. Now 8.15, extremely sorry. Now we know the initial velocity, we know the deceleration. So the formula which for the linear motion, it says v square minus u square equal to 2as, right? So here the final velocity v is 0 since the body is coming to rest. U will be equal to this velocity which we found out right now. U will be equal to this. Let's take this as v naught to avoid the confusion. Right. So u we know the acceleration a which will be equal to minus of d. So let's write down minus a equal to d. Since there is a deceleration, there is the negative sign involved over here. Right. So now we come down to the displacement s is equal to, we can write it down as v naught square by 2d.
Right.
Putting in the values, we find out that s is equal to 1.22 meters, which is the required displacement.
Okay. So in this question again we saw the combination of translational and rotational motion, as well as there was a rope also. So the concept tension also was involved. So these kind of questions are quite important from JEE point of view. That was question number 7.